Okay. So good evening, everyone. Welcome to your fifth discussion session in Mechanical Behaviour of Materials. I am Pragyandipta Mishra, PMRF scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. And today we'll be discussing about plastic instability, the role of strain rate in flow stress, and introducing us to the concepts of dislocation. This will be followed by some problems on these topics. So with that out of the way, let's begin our discussions for today. So the first thing that we will talk about is plastic instability. Now, what do we understand by the condition of plastic instability? We already have got an idea of what is plasticity, right? In the previous class, we have discussed about what plasticity is and how this influences the material behavior. Now then, what could be plastic instability? So if you think about it, if the plastic behavior of a material in effect is unstable, right? Meaning that you are not getting a stable plasticity zone, but instead you are getting an unstable or unstable plastic condition, and the deformation happens in such a way that you do not get a behavior that you commonly associated it with, right? Essentially, what do we understand by instability or instability in the condition of loading or in conditions of stress and strain? Now, what we commonly associate stress and strain with is that whenever we are applying deformation, it becomes much more difficult for us to apply the next deformation because of the rising stress, right? Because as we go up and up in strain, the stress would also correspondingly increase, right? Because that is the general understanding. However, we see that after a point, the stress strain curve do not follow that path. Now, with increasing deformation, the stress value continuously starts falling, and therefore the plastic deformation will continue under falling load or pressure. Now, this is essentially what we are defining as plastic instability. Okay, this is the region in the plastic behavior of materials, or the plasticity part of the stress strain curve, where the plastic deformation continues even under falling load or pressure. So let's write that down. Would continue under falling load or pressure. Okay. So, why does this happen? Why would we see this happening? So, essentially, what is happening during plasticity? So, till now, we have not gotten introduced to the concept of dislocation, so it is not very straightforward for us to define what happens during plasticity. But you can say that during plastic flow or plastic flow itself, you can use plastic flow as the word because you don't know dislocation motion yet. But during plastic flow, what will happen is at some points, right, you will have instability forming because there will be regions where, like pockets of region where it becomes very easy for dislocations to move through. Okay, once you reach those pockets, it becomes the plastic flow becomes very smooth, and then the amount of stress that you need in order for that flow to happen reduces. Okay, initially there will be a lot of resistance to that plastic flow, but once you reach those regions, once you reach those instability points, the deformation starts occurring very easily, and therefore it becomes very easy for you to ensure that plastic flow continues from that point onwards. Okay. One important characteristic of plastic instability is that your uniform elongation that you are seeing till that point would now cease to exist. Right now, you will not have a uniform elongation. Instead, the elongation would be very drastic, very dramatic. Okay, so there'll be like different ways you can characterize this, but like the elongation would not be uniform anymore. The elongation would suddenly like start moving in a very different way. Okay, so this is another point that you can note down. Uniform elongation ceases. And if we draw the stress strain curve for this case, okay, so how it will look like? So let's say if stress strain curve is something like this for any general material, let's make it a little bit. Right, if this is a stress strain curve, for instance, now this is a representative value, you won't get exactly like this, but let's say this is a stress strain curve. Now this is the point where your instability would start, right? Because now the stress value is falling, even and the plastic deformation is still continuing, right? So you don't have increasing stress value with increasing plastic deformation. The deformation would still continue under falling stress or falling load, right? So what could we say about this point? Let's say this point is called point of instability. Okay, let's call it as point of instability. So what happens at point of instability? What could we say about point of instability? That is something that we can tell in terms of mathematical relation, or something that we can find out in terms of that. Let's say if I want to take the slope at this point, some slope df, what will that be equal to? Now as you can see that this is the point where the sign or direction changes, right? So therefore the slope would be 0, right? Because the line, the slope that you're drawing is parallel to the x-axis, so slope would be 0. And one more thing that you can say here is, if you say that this is your elongation that is happening, so your this region will represent your uniform elongation region. Okay, let's write down that point about point of instability. So at point of instability, the force is maximum, right? Force or stress. Just a second. Let's see. Yeah, okay. So as I was saying, at point of instability, your force or stress is maximum. Therefore, your slope or df would be equal to 0. So if we want to solve this and get a relation between your strain and stress, so you can write it in this terms. So we know from our previous class that the flow stress would be represented as k times epsilon to the power n, right? And we already know F is equal to sigma times dA, right? So at point of instability, what is happening? dF is equal to 0. Right? Therefore, if we differentiate this equation, the equation 1 that I have represented here, if I differentiate that and equate that to 0, I'll get something like sigma times dA plus, okay, let's not write it as dA here actually, let's write it as A only. Yes, sigma times A. Okay, sigma times dA plus A times d sigma is equal to 0. So this is something that we can immediately write. Now rearranging this, we will get a relation like d sigma by sigma is equal to negative of dA by A. Right? So let's represent this by equation number 2. Okay, let's keep that equation there. Now another thing that we can write is change in strain value, okay, is equal to dl by L. Right? But if you are saying that the area, like the volume remains constant, or dV is equal to 0, then we can write AL, dA of AL is equal to 0, or dA times L plus A times dL is equal to 0. Or in other words, dL by L is equal to negative of dA by A. Right? This is another relation that we can write. So here, your change in strain, let's move this entire thing. Let me just move this. Move this on top, yeah, so that you can have a clear flow of thought. Okay, so now if I come back to my d times epsilon, it is equal to dl by L, which is equal to negative of dA by A. But on top, from equation 2, we have already written dA by A minus negative of dA by A is equal to d sigma by sigma, right? So if I use that, it will be d sigma by sigma. Or in other words, if I rearrange, I can write sigma is equal to d sigma by d epsilon. Right? So let's write this as equation number 3. So this is one relation. Okay, let me add a few pages. Right. Should be sufficient. Okay. So we already have the flow equation, right? K times epsilon to the power n is equal to flow stress. Now if I use that, then d sigma by d epsilon would be equal to K times n into epsilon to the power n minus 1, right? And if I substitute this back in this equation number 3, it will be sigma is equal to K times n epsilon to the power n minus 1, or K times epsilon to the power n is equal to K times n epsilon to the power n minus 1, which will lead to epsilon is equal to n, right? So this is the condition for plastic instability. Or how do you find, if somebody gives you a particular material and asks you to find what is the value of n, right, K, for in the flow stress. So how would you find that value of n for the flow stress? This is a way you can find it. You can find the point of instability, find the corresponding strain for that point of instability, and that is what is equal to the value of n. Okay. So this is one thing that you can keep in mind. Okay. Another thing that, because this is the proof that we already got. From here, what we can say is that as we increase the value of n, the elongation will increase, right? So for some reason, if you see that the n value is higher, you can automatically say that the total elongation would be higher, because n will define where the uniform elongation point will lie. So as you can see from this graph here, n is basically defining where your uniform elongation point is. If your uniform elongation point is larger, then your total elongation would also be larger, right? So that is something that you can automatically see as a consequence of this entire exercise. Okay, so let me write that down. As n increases, total elongation will increase. Since the uniform elongation is also increasing. So I can write that bracket, since the uniform elongation is also okay. So this is about plastic instability and how you find the condition for the value of n, right? So for in flow stress, what is the value of n? If you want to find, this is the way you can find it. Okay. Another thing that you can see, if you are plotting stress versus strain, okay, and on the stress side you're also plotting d sigma by d epsilon. Both you're plotting. Okay, let me use a different pen. So I'm plotting stress, strain, and d sigma by d epsilon both on the stress on the y-axis, and along with that d sigma by d epsilon also on the y-axis, because both have the same units. So my stress strain curve would look something like this, right? My d sigma by d epsilon curve would look something like this. Okay. So this is governed by the equation sigma is equal to k times epsilon to the power n. This is governed by d sigma by d epsilon. So the point where they both intersect, this point is known as instability, the point of instability. Okay, so this gives you that value. I'll just write it as py, point of instability. Okay, so this is where your necking will start, essentially. Okay, and this value, that n value that we are trying to look for, will range around 0.1 to 0.6 for most of the material system that we are looking for. Okay. Another important feature of this value of n that we can immediately look for is what if the value of n is higher, or what if the value of n is lower? So what would that signify? So say if you have higher value of n, let's draw and see how that looks. How would the curve look like if the n value is higher? So you will have this kind of curve if the n is higher. But if your n value is lower, then your curve would look something like this. We'll use a different pen. Let's assume that the elastic part is same. So from here, the curve would look like this. Okay. While this was a longer drawn out curve, this dips very quickly. So this is how your higher n and lower n values would look like. Okay, let me just point it out. Higher value of n and lower n. Okay, so essentially what is happening is, if your n value is low, then work hardening rate is initially very high. Okay, but the rate will decrease very quickly or very rapidly with the strain. But the rate decreases very rapidly with the strain. Let's not write very rapidly, let's just write rapidly. Rapidly with strain. Okay. So as you can see from the graph, at lower values of n, your work hardening would be very high initially, which means that initially itself you will get a very large peak, as you can see here in this graph that I have drawn. But it will rapidly go down. The rate will rapidly go down as we increase the strain. Okay, so this is something that you can note. On the other hand, if n value is high, so if you want to see the vice versa, if n is high, okay, work hardening is initially less rapid. Okay, so initially your work hardening value will be less rapid, as you can see from the graph. Okay, but it will continue to rise with higher strain. To high strain values. Okay. So this is what we can take home from test plastic instability. All this part is anything else that is over and above this is anyways like another concept that we can talk about, but this much is sufficient for you to understand in terms of plastic instability. The major reason why we're studying plastic instability was to get an idea of what this value of n could be, right? Now this n value, once we are knowing, then it is sufficient for us to understand like anything with in relation to flow stress. So the reason why we are doing plastic instability or we are understanding plastic instability is so that we can characterize this value of n. Okay. Okay. So now that we have done with plastic instability, let's move on to the next concept, which is effect of strain rate on flow stress. Okay. So effect of strain rate. Now, why do we need to understand the concept of strain rate? We already know what is the relation between strain and stress, right? Flow stress with respect to strain, how that is flow stress is how strain is influencing flow stress. Why do we need to understand the effect of strain rate also on flow stress? What could be the major reason? Now, if you want to think about it, right? So, what does strain rate exactly contribute towards in uh, any kind of deformation or any kind of any kind of stress or deformation? What the strain rate is actually contributing towards? So if you look at it from a different perspective, okay, let's not even go into dislocations, okay, because we have not looked at dislocations yet. But if you look at it from a different perspective, just with respect to materials, and you're looking at it from outside view, if you're deforming the material, right, and you're pulling it slowly versus if you're pulling it fast, there'll be a noticeable difference in the way the material will respond to your behave to the load, right? What happens when you pull the material slowly versus what happens when you pull the material fast? Think of it in this way. Do we need to supply more amount of energy? Do we need to expend more amount of energy to do something fast compared to something that we need to do slowly? So you think at it like this. If you think from perspective of energy, what exactly are we looking for when we say something is being done fast or something is being done slowly? If something is being done fast, then we would say that the amount of energy or would be higher, right? Because you're looking at it from the perspective of kinetic energy. You're applying a short amount of energy, like you're applying a large amount of energy at a very short interval of time. That's what you're trying to do, right? So when you're trying to apply the same concept here, what you would expect? If the strain rate is higher, which means that you are applying strain at a very fast rate, then you would need to expend a little bit higher amount of stress in order for you to ensure that that happens, right? So there is a relationship between strain rate and flow stress. So we can write that in terms of a constant known as M, which is the strain rate sensitivity. So let's define that first. So rate of deformation okay, what is rate of deformation here? Is given by d of ln of sigma divided by d of epsilon dot. Now that is equal to m. Now here epsilon dot is signifying strain rate, okay, and m is strain rate sensitivity. Okay, so if you want to write this in relationship form, this would be sigma is equal to c times epsilon dot to the power m. Okay, now this c and m are different from whatever we saw in the flow stress equation. Okay, there we saw k and n, right? They are very different from this c and m because this is relating the flow stress to the rate of strain rate, while that was relating your flow stress to the strain value directly. Okay, now one thing that you can note for this equation is that this m strain rate sensitivity parameter m usually will range from 0 to 0.03. Okay, so that is the general range for strain rate. So what does that imply? If your strain rate sensitivity parameter is so low, what will it imply essentially? If your strain rate sensitivity parameter is not giving you a very high value of strain, even at higher, like even at some particular value of flow stress, then you need to apply like a large amount of strain in order to achieve even a small change in flow stress, right? Imagine you applying some value, let's say 10 or 100, right, as strain rate. Then because it's to the power 0.03 or 0.01, right, the entire value reduces to such a small value that your flow stress would not change appreciably. Okay, so if you want an appreciable change in flow stress, you need to apply very high values of strain rate. Okay, so if I want to write that down as a point so that you can remember, strain rate needs to change appreciably to cause a significant change in flow stress. Okay, so this is something that you have to keep in mind. You need to change your strain rate value appreciably. So you would say that, okay, I am doing this test at say X value and then I change the strain rate to 2X, but I'm not seeing a very big change in flow stress. This is because of this region. Your strain rate sensitivity parameter is essentially very, very small. So that does not change your flow stress too much as you change the strain rate. Okay. However, there is another way in which you can influence the strain rate sensitivity parameter. Strain rate sensitivity parameter, it is dependent on temperature. Okay. So if we define a melting temperature Tm, okay, for T for temperatures greater than 0.5 times the melting temperature, your M value will increase to 0.1 to 0.5. Okay. M increases to 0.1 to 0.5 range. So this is the new range if you increase the temperature to this range. Okay. So this is something that you can do in order to, so if you see if you want to ensure that your flow stress is getting influenced by strain rate, like if you want to ensure that that happens rapidly, if you want to ensure that that happens rapidly, you should increase the temperature to higher than at least half of melting temperature. So if you increase it beyond that, you will see that there's a sharp rise. Okay. So if I draw this curve here. Okay, so essentially if we are having T by Tm on this axis and M on this axis, initially you'll see strain rate to change like this with temperature. Okay, until it hits the value of 0.5. After which, beyond which, you will see that the value changes rapidly like this. Okay, so M value will change rapidly once it hits this 0.5 value. Okay, so this is something that you can keep in mind. Now there is a very important significance for this value of M. Okay, what happens if the value of M becomes very large? We'll come back to that. But before that, let's see how we can measure this value of M. Ways to measure M value. So there are two different ways in which you can measure. Both of them are actually relying on the same principle, but it's just like two different ways that has been defined to measure it. One is you measure your flow stress and strain at two different strain rates. Okay, so for instance, you draw this kind of graph. So you have one strain rate, you have another strain rate. So this is epsilon 1 dot, epsilon 2 dot, right? So your flow stress versus strain. So at the same value of strain, let's say I drop a line like this. Okay. So at some particular value of strain, if I'm measuring the stress values for both epsilon 1 dot and epsilon 2 dot, both the cases, then I can use that information to find my constants, right? C and M from there. In a similar vein, if I do the experiment in a different way, now instead of applying two different strain rates, what I will do is apply stress versus strain at one particular strain rate. Okay, and then change the strain rate. So there'll be a sudden change to a new value. Okay, so this is at epsilon 2 dot. This is at epsilon 1 dot. So I'm doing a sudden change. Now in both the cases, the way I'm finding the values, the constant strain sensitivity parameter and C value, both of them, I can find in the same way. So what we can do is we can write sigma 1 is equal to sigma 1 corresponding to your case 1 where your epsilon dot was 1, sigma 2 corresponding to epsilon dot 2. Okay, so sigma 1 will be equal to C times epsilon 1 dot to the power M, right? For curve 2, we'll have epsilon 2 is equal to, sorry, sigma 2 is equal to C times epsilon 2 dot M, right? So these are the two relations we'll have. Now if we divide the equations one by the other, we will get, let's just write it down. So this is 1 and 2. Now if I do 1 divided by 2, I will get sigma 1 by sigma 2. On the right hand side, C gets cancelled. So we will have epsilon dot 1 by epsilon 2 dot whole to the power M, right? Or further, if I want to simplify in terms of M is equal to, so this would look like something like this. M is equal to ln of sigma 2 by sigma 1, right? Divided by ln of epsilon dot 2 by epsilon dot 1. Alright? So this is my relation. Okay, so both the cases we can use the same relation. Okay, here in the first case I am defining at some particular value of epsilon naught where I'll measure the sigma 1 and sigma 2. Here this is already defined, predefined, where I'm changing the strain rate, right? The strain value where I'm changing the strain rate suddenly, that is where I'll measure it. Okay, that is where my epsilon naught will. Okay, I hope till here it is clear. There is no doubt how we are measuring these values. How to measure n in the previous case, now how to measure m. I hope these things there is no doubt. Okay, so with that, let's move on to. Okay, let's move on to. I will not move on. Let's come back to our previous case, right? We were talking about the value of m and what significance does the carry. What significance does it carry? So significance. Okay. So very large values of m would lead to something known as superplasticity. So we will define what is superplasticity. Let's just first write it down. Leads to okay. An interesting term, right? Superplasticity. Now, what do we mean by superplasticity? So, what exactly is happening at high strain rate? Essentially, if your strain rate is very, very high, your deformation, any deformation would result in like large elongation. Okay, any deformation would result in large elongation at low stress value. Okay, and this happens without the material failing. So essentially, why we are calling it superplasticity is that the plastic part, the plastic region now elongates suddenly. Like you will have a large amount of plastic region because now your deformations are resulting in very large elongations at very low change in stress values. Okay, and failure is also getting postponed to a very like later stage. Okay, so if I want to define superplasticity, it's one word. So you can say it is just deformations that result in very large elongations. Okay, so deformations that will result in very large elongations. That is one part. Second part is, so your strain part you're covering. Second part, stress value will also be very low. So at low stress values or at low stresses. At low stresses without the failure of the material. Okay, so sometimes you will see that your because of this high value of m, right? Because essentially, if you increase the temperature so much that the m value increases so much, like to a very large range, you will see that your engineering strain value, okay, increases to 20 times its original Okay, so you can elongate it 20 times as compared to whatever elongation that you were seeing before. So this is very useful in some applications, right? Because you want to draw out materials. You want to ensure that your you want to draw out wires or you want to roll out sheets, right? So for these cases, you want to ensure that they become very thin and they become very long. So in those application cases where you want to see those particular use case, you would ensure that your temperature remains very high so that your M values goes up and therefore you will see a large amount of elongation. Okay. So this is another thing that you can remember. So now that we talked about superplasticity, let's talk about what could be the conditions under which the superplasticity could exist. Okay, this is something that you can also note down. Because this is a major use case, a major like, for lack of a better word, a major application, you can say. Okay, not exactly application, but it's like superplasticity is majorly applied for a lot of applications, so that you can get some certain features out of a particular material system that you're looking at. So therefore, you need to understand what conditions the superplasticity operates at. Just increasing the value of just increasing the temperature above a certain threshold is not the only case that will lead to superplasticity. You need to have other things also. So let's understand those conditions. Okay. First thing is, you need to have extremely fine grained and equiax grains. Okay. So what does that mean? Extremely. Let me write it down first. Fine grained and equiax structure. What does that mean? It means that you cannot have large grains. You cannot have grains which are like having compositions made out of large unit cells. What do we mean by grains here? So there are multiple different defects which are present in a material, right? Now, when you are trying to create a solid from a liquid, right? Let's say you melt a material and you want to create a solid out of that material. How does it become solid? Say you have liquid. Let's say this entire thing is liquid. Okay, this is something that you don't have to remember, but I just want to explain so that you understand this concept better. What do we mean by fine grained and equiaxial? Let's say this entire thing is liquid. Okay, this entire thing is liquid, and what I'm doing is I am slowly cooling it down. Okay. Now, when I cool it down, at some points the cooling would be a little bit faster, and you will see that at that point, initially itself, that point, the grain will start forming. Okay, so what do we mean by grain is like a small particle that forms, which consists of multiple of those multiple atoms or multiple unit cells of atoms, which are arranged in a particular format. Okay, so you'll see that grains start forming here, right? Now these grains will start growing slowly and slowly. It will start growing. Okay, so this grain will become bigger and bigger, slowly, and similarly other grains will also become bigger, and they will they will grow till they reach the next grain, till they hit the next grain. After which all the liquid it becomes solid. Okay, so you can understand that all these grains are growing simultaneously, and they will hit each other at some point, and they will become like individual grains. Now, what we mean by fine grained structure and equiax structure, meaning that the grains are so small. Okay, so at the end, the growth is so slow, and the grains are so small that you will have lot of grains, and they are almost similar in size. Okay, so that is something that you need to achieve for superplasticity to even bigger. Okay, so this is one thing that you have to keep in mind, one necessary condition. Another case could be, of course, like the one we have already talked about, that is one more important point, that temperature should be relatively high. Temperature should be relatively high. So let's say it should be greater than 0.4 times Tm. We already discussed about this condition, right, in detail. So we'll not elaborate on that. So this is one more condition. Another thing would be that your strain rate should be low, meaning that you should not increase your strain very quickly. You should slowly increase your strain rate. Then only you'll achieve superplasticity. And finally, your microstructure should be stable. So microstructure should be stable. Now, what do we mean by that? Microstructure should be stable. It means that as we apply this elongation, right? As we apply the deformation, it should just keep elongating. It should not split suddenly, because if the microstructure is not stable, then you might have those sudden split or sudden like break in the system, and then it will fail immediately. You do not need that failure to happen, right? You want the plasticity to keep continuing for a very long time. So a microstructure essentially should be stable. That is why we are talking about the stability of the microstructure. Okay. So finally, let's talk about, now that we know that there's a relation between stress, flow stress and strain, and flow stress and like some strain rate. So let's write a combined equation that takes into account the strain and strain rate together. Okay. Combined effect of strain and strain rate. Okay. So we can write flow stress to be equal to some C. Okay. Some C. We will not define this constant C, just some C. Epsilon to the power n and epsilon dot to the power n. Okay. Now this is the relation that we can finally define for flow stress, how that is related to your epsilon and epsilon dot. Okay. Now, of course, necessary condition for this to happen is you have to assume that temperature is constant. Right, because if temperature changes, then your strain rate or like other things, m parameters, etc., will change, right? So that will influence your behavior. So based on this discussion, one final thing that we can note is that effect of temperature, right? How temperature influences your behavior essentially. So if you are having higher temperature, what can we expect? Your T is high. So let me draw this graph. Stress versus strain. Okay. So if I draw like multiple graphs like this, what does this represent? This this direction. What does this represent? As the stress value keeps increasing with it keeps increasing with increase in temperature, or does it keep increasing with decrease in temperature? What does that signify? Now think about superplasticity. What is happening at superplasticity? The ductility is increasing, right? With at lower stress value. So with increase in temperature, your stress value will decrease and your ductility will increase. So this signifies increasing strain rate or decreasing temperature. Or decreasing temperature. Okay. So another relation that we can write and remember for future reference is how do we relate the strain rate with temperature? How does that vary with temperature? Okay, because now that we have seen that temperature plays a very important role, so how will we relate strain rate with temperature? So there is a very useful equation which can be used to give this relation. Okay, given by Zina Holloman. So I'll just write down the final equation. I will not write the whole thing, but Z is equal to epsilon dot, okay, exponential of Q by RT. R is the gas constant, Q is the activation energy for plastic straining, T is the temperature, epsilon dot is the strain rate, and Z is the constant, the Zina Holloman constant. Okay, so this thing is something that you can remember. Q is your activation energy for plastic strain. Okay, activation energy for plastic strain. So this is it with respect to our discussion on effect of strain rate on flow stress. Now let's move on to our last discussion for today, which is introducing us to the concepts of dislocation. Okay, we'll not go deep into dislocations because we'll be discussing that in the further classes, but we'll just have a basic idea what exactly is dislocation and why we are actually studying this dislocation. So now we have continuously come up or heard this word, like I have talked about it multiple times that there's something known as dislocation that is influencing the plastic behavior. Now we'll understand how that influences the plastic behavior. Okay. Dislocation. Okay. So dislocations are crystal defects which are present in any material system and influence the plastic flow of that particular material system. Now, why are we talking about dislocations in the first place? Essentially, if there were no dislocations, then what would happen is the material, as we keep pulling the material, as we keep pulling them apart, at some point the bond between the atom will break and the material will just fail suddenly. Okay, so you'll just have an elastic region and then failure. There'll be no plastic region, there'll be no plastic flow. Okay, dislocations are what is influencing this plastic flow. So, how do we define this dislocation, or why do we say that dislocation would exist, right? So let's look at the energy curve for any particular material system, right? So if we have something like this, Let me just draw it two direction. So, okay, let me draw the atoms first. So say that we have a crystal structure like this. Now this is layer A, layer B, and layer C. Now if I want to move layer B, right? Or let's say I want to move layer A in some particular direction. I want to move the layer A in this direction. I'm applying a shearing load. Only layer A I'm moving with respect to layer B and C. Okay, what will happen? Let's track one particular atom. Let's say I just shared this atom. I want to track how this atom will respond. So I've shaded one atom, right? I'm tracking how that atom's energy will change as we move. Let's say this is the initial position. Okay, this is the initial position. Right? So as we move, the energy will go from the lowest possible value, because that's the position that it occupies normally, the lowest possible value, to some value which is higher, then come down again to the lower possible value, right? So this entire range that I've drawn here, you can draw it a little bit more. This entire range that I've drawn represents this distance, right? Because this shaded atom in blue and the shaded atom in red, this position, this shaded atom in blue and shaded atom in red, represents the two possible equilibrium positions for this atom, right? So if the layer moves such that the atom blue reaches the atom red, then you have reached from one equilibrium position to the next equilibrium position, right? So your energy would be minimum at both of these points. So let's say this is atom blue. I'll represent it by, let's say, this position by P and this position by Q. So this is P and this is Q. Okay. So your energy would change in this fashion with distance. Let's say this is X, the distance. Okay. Now this is how your energy changes. The middle point, basically the highest value, where you have the highest value of energy, would represent this point P being at point R, right? So this is point R. This is point R. Now this point R is essentially just on top of the atom which is below the layer, right? So there it will be very difficult for you to accommodate the atom, because already one atom is there in the layer below. So they will strain each other. So it will be very difficult. So the amount of energy required would be the maximum there. Now if I want to draw force, right? Force is what? Like if you differentiate energy, you can draw force, right? Or stress, if I want to draw shear stress, because stress and force are directly related because it's just by area. So if I want to draw the stress graph, how will that look? Now stress would be something like this. It will go up. It will go to 0 here. Then here, right? So this is my point Q. There's not exactly, I've not drawn it exactly to scale perfectly, but yeah, this is my stress, shear stress curve. Okay. So what am I seeing? That between one, like the motion of atom from one position to the next equilibrium position, I'm seeing a sinusoidal kind of wave, right? So if this was B, this is that B, right? P and Q. So I can write the variation in stress in a sinusoidal form. So how people usually write it is like this. Tau is equal to tau max times sine of 2 pi x by b. Okay, b is the equilibrium, the distance between the equilibrium positions of the atom. Okay, x is the distance the atoms are moved, so that you go from, like, you whatever each position, each point is defined by x, from whatever position you started till the point you have moved, that is x. Now, okay, let me just actually write it down, otherwise there will be confusion later. Tau max is theoretical strength of the crystal. Okay, the maximum value that tau can achieve. So this is my tau max here. Theoretical strength. Okay, x is distance the atoms are moved. Okay, b is distance between the equilibrium position. Okay, so x is very much smaller than b. You can think of it that way. Okay, so since x is very much smaller than b, we can write tau is equal to tau max times sine of something. That something is very small, so I can write it as sine of something is equal to sine of x is equal to x, right? We can write it in that form. So 2 pi x divided by b directly without writing the sign. Now this x by b is representing what? It is representing my strain, right? So I can write x by b is equal to strain. Okay, so tau is equal to g times strain. Okay, so if I substitute this back, what I will get here is tau max is equal to g divided by 2 pi. So this is the theoretical value of maximum strength that we can observe. Okay, theoretical strength that we can observe for a particular material system. Just a minute. Yeah. Okay. So this is the theoretical value, and people have said that actually the realistic range in which the theoretical strength would lie is somewhere around g by 30. Okay. So let's say that it is in that range, g by 6 to g by 30 range. Okay, that your maximum tau maxes should lie in, right? However, what we see is in real life, this is not even close to the range in which this entire value would lie. Okay, this is not even close to that range. Sorry, I'll mute you. Okay, this is not even close to the range in which the theoretical value would lie. Now, why that is the case? Because there are defects which are present in the material system, and that defect influences how this entire expression is going to be. And these defects which influence this strength value is known as dislocation. So dislocation essentially makes it easier for us to deform the material. Otherwise, it will become very difficult for us to deform the material. We will have to keep applying load till we reach some very high value, after which the failure would be very sudden. Okay, so dislocation essentially helps us in ensuring that the plastic flow happens, the ductility happens, and the material starts deforming before it fails. Okay. So this is how people discovered that this dislocation was actually present in the material system. Okay, and they were able to convincingly prove that dislocations are present in any system. Okay, what people have observed in any like when they observed it under microscope, what they saw was that there were dislocations which are present in this form. Okay, so you will see that if there is atoms which are arranged in certain way, now due to the dislocation, okay, due to dislocation, you'll see that the atoms are not exactly arranged perfectly because of this presence of dislocation, but you will see some kind of steps being formed. Okay, you will see something like this, and then you will see some other kind of atoms, like the atoms will have some other positioning which will be filling up this atom region. Okay, this is what people have observed in under microscope. So this kind of step essentially proves that dislocation is actually present within the microstructure, and this gives us an idea of how the dislocation would be looking like in real life. Okay. The next concept is types of dislocation. Actually, we can skip that for time being because no, actually we'll need it. Actually, I think for this. Okay, yeah, we'll do it. We'll do it. It's okay. So there are two types of dislocation. Okay, let's quickly go over those types of dislocation, and we can move on to problems after that. There are two different types of dislocation, which are known as edge dislocation and screw dislocation. Now, essentially, when you study, like when you look at dislocations from a microscope, under a microscope, you will not be able to distinguish between what an edge dislocation or what a screw dislocation would be looking like, because you'll have a mixed characteristics within the dislocation itself. Okay. Essentially, why we are defining this edge and screw is because based on how this dislocation could be formed, we want to say this particular dislocation is having an edge characteristic or having a screwed characteristic. Okay. Now in edge dislocation, what we'll have is, let me just draw this thing. You will have an extra half plane of atom. Okay. Extra half plane of atoms. Okay, so how this will look like is, let's say I have 5 atoms in the first layer. Next layer will also have 5 atoms. Third layer suddenly has only 4. Then consequent layers only have 4 atoms. So there is one layer here which does not have a corresponding. So this exactly does not lie below those atoms. This will suddenly shrink a little bit. Okay. So here we'll have formation of a dislocation. Okay. So edge dislocation is represented by this T or the reverse T symbol. What we can say is in edge dislocation, we have an extra half plane of atoms. Okay. But if you're seeing it in 2D, you will say that it is an extra line. Okay, not extra half plane, but a line. But in 3D, that entire thing, like it'll percolate throughout the, like it'll percolate like this. Throughout this extra half plane will percolate throughout the 3-dimensional case. So in that one particular plane, you will see that entire plane of atoms are not having another layer below it. Okay, so this results in the dislocation being formed. Okay, so your line vector, your U, for this dislocation line is in this direction. Okay, so U essentially is the line vector, dislocation line vector, and there's something known as slip vector or Burgers vector, okay, which is known as B. Okay, now this essentially is the shortest lattice translation vector. Okay, shortest lattice translation vector. So what do we mean by this shortest lattice translation vector? What do we mean by that? It means that the line vector and like if we are trying to complete a region around this location, let's say I define this region. Let me use a different. Yeah. Let's say I'm defining this region. I moved 4 times in the right direction. Then I moved 1, 2, 3, 4. 3 times in the bottom direction. Then I moved 4 times back. I'm not able to move 4 times back, right? So let's say there is an extra atom here. Okay. Let's say I'm defining an extra plane here. So if I move 4 times, then I move 3 times up again. Then there is one missing link right here that closes this vector. So this is that shortest lattice translation vector that will close the loop that we are starting around the dislocation. So that is known as the slip vector or the Burgers vector. Okay, the extra vector that closes the loop, that we call it a slip vector or Burgers vector. Okay. So this is edge dislocation. If we want to define a screw dislocation, so in edge dislocation, what is happening is you are splitting the crystal in such a way that you have an extra half plane of atom. In screw dislocation, what is happening is you have say this kind of structure. Okay. Okay. And you will have okay. So this part, this region, let me use different pen, that we are obtaining when we are twisting the crystal. So essentially in screw, what you're doing is you're holding the crystal from 2 points. Like you imagine it happening in this way. You're holding the crystal from top and bottom and you're twisting it like this. Okay. So if you have played with Rubik's Cube, you can imagine screw dislocation very easily. You are just twisting the crystal, which will result in the formation of a screw dislocation, a dislocation plane which is outside the, like an extra plane which is outside because you have twisted it. Okay. So you will see that your dislocation line would be in this direction and your Burgers vector would also be in this direction. So your dislocation line and Burgers vector are essentially parallel in screw. So yeah, I forgot to mention that in edge. In edge, your dislocation line and Burgers vector are perpendicular, right? You can see that the Burgers vector is in this direction. This direction is your Burgers vector. Your U is in this direction, so they are perpendicular to each other. However, in screw dislocation, they will be parallel. Yeah. Parallel to the Burgers vector or slip vector. Burgers vector or slip vector, they are all same thing. Okay. Now, depending on whether you're twisting it in one particular way or the other, okay, if you're advancing one plane after like after clockwise rotation, versus if you're advancing like one plane after like if it goes back one plane after clockwise rotation, you can call it right-handed screw or left-handed screw. Again, that we will come back to that later when we need that, but you can just remember that there is right-handed screw, left-handed screw. Okay, so this is another type of dislocation. So Burger's vector already I have defined, so I don't think we need to go back to Burger's vectors again. So with this, we will come to an end for discussion for all the things that we need in this week. Now we will move on to the problems for today. Okay. Let me just give me a second. Okay. Just let me check if I missed anything. Just check. Okay, I think Burger's vector I talked about how it is shortest lattice translation vector, slip vector, direction in which net displacement occurs. I just showed you how that happens. And vector that completes or closes the Burger circuit. Yeah, so that is Burger circuit. So let's move to the problems for today. Okay, so this is the first problem. They are telling for a material exhibiting necking under uniaxial tension, the true stress at a point of maximum load is given by the expression. Okay, so they are asking us which expression or expressions gives us the true stress among these four expressions that they have given us. Okay, so let's try to derive this expression. I think we have already derived a part of it previously, but let's do it again just for the sake of completeness. Okay, so for a material which is exhibiting necking under uniaxial tension at the point of maximum load, what we will have? We will have df to be equal to 0, right? We already discussed why force the slope is equal to 0, right? Like slope, the force is maximum or the slope df will be equal to 0, right? Which will imply that d sigma a will be equal to 0, or sigma times dA plus a times d sigma to be equal to 0, which will result in d sigma by sigma which is equal to d minus dA by a. So this is one part, one equation. Now the second part would say constancy of volume, right? So dV will be equal to 0, constancy of volume, right? The volume is constant or change in volume is equal to 0. So A dl, like a volume is equal to A times L. So A dl plus L times dA will be equal to 0, or dl by L will be equal to negative of dA by A. So this is equation 2. Now dl by L is also called d epsilon, right? So I can write d epsilon here directly. So from 1 and 2 I can write d sigma by sigma and 2, d sigma by sigma is equal to d epsilon, right? So if we rewrite this, it will be sigma is equal to d sigma by d epsilon, right? So this is one expression. So let's see if this expression is present. Yes, it is there. first one. So I can tick that one. Now, if you want to further see in terms of, so there's another expression they are writing in terms of true strain, engineering strain. So let's see if that expression could also be valid. So if I can write d sigma by d epsilon to be equal to d sigma by d e, okay, d sigma by d e into d e by d epsilon, right? So it will be d sigma by d e times dl by L naught divided by dl by L. So if I cancel out dl and take L to the top, it will be d sigma by de times L by L naught. So L is equal to L naught plus dl, right? So it will be 1 plus E. D sigma by de times 1 plus E. Right? Therefore, this is also one of the solutions. So let's see if that solution is present. Yes, the third. So both of them are giving the correct answer. I hope there is no doubt as to how we are arriving to this relation. Okay, so let me move forward to the next question. Which of the following metal working process? Okay, let me show you. Which of the following metal working processes involve very high strain rate? So they have given us some processes and they are asking which of them will involve very high strain rate. Now, again, this is not a question that will, like a problem that you are solving from the concept that you have studied. This is just something that you need to know which kind of engineering processes use this high strain rate concept that you have studied. So the first one, of course, is sheet rolling. We know that that involves very high strain rate. Wire drawing also involves that, right? Because you need to have that kind of processing so that you can get that rolling and drawing. Like you can have wire being drawn out or sheet being rolled out. You need to have high strain rate. Otherwise, the material will not draw to such thin wires or thin sheets, and you will see that the entire material will either fail before it reaches that thin sheet or wire, or it will not reach that level of thin, like that level of thinness that we want to actually get. Okay, thinness is not exactly a word, but like I don't have a substitute word for that. Other than that, equal channel and angular extrusion will not involve that. You're just extruding a material. You will not need to have high strain rate in that case. Similar in sheet bending, you already have the sheet. You're just bending it. You don't need high strain rate in that case. Okay. Next, they're asking what are the necessary conditions for a material to exhibit superplasticity. We have already discussed this in the discussions part. So low strain rate was one of the things. High temperature, of course. Extremely fine grained microstructure. I have already explained why fine grained microstructure is necessary for this to happen. Because if you don't have fine grains, then your plasticity would suddenly fail. Because if you're having grains which are very big grains, then what will happen is the grains will start splitting at some point. If you have fine grains, then they will actually accommodate this plasticity within the regions. So you need extremely fine grained microstructure. And you also need high strain rate sensitivity, high value of M. We have already discussed that. So all four of the options are required. Next question is also again another conceptual question. If strain hardening exponent is large, okay, N, not M, we are not talking about M. Strain rate sensitivity parameter, we're not talking about that. We're talking about strain hardening exponent. If that is large, then we can say work hardening rate is initially less rapid but continues to high strain. That is correct. We have already discussed what happened. What is the consequence of high value of strain and low value of strain? I've already explained that. So yeah, I hope like you have understood why we are saying this. With the graph we have seen how high value of N will lead to work hardening stress being initially less rapid but leading to high value of strain. The other options, work hardening rate is initially very rapid but limits. No, that is for low value of n. And then work hardening gradually increases to high strain. That is correct, but but you also need to have that initial less rapid part. So it does not mention the initial less rapid part. It is only mentioning the other half. It increases gradually to high strain value. So that is correct, but it is half correct. And finally, work hardening is initially very rapid but continues to high strain is completely wrong. It does not happen in any case, whether the n value is low or n value is high. Okay. So I hope all these conceptual questions you have understood directly. No doubts there. So let's move on to the next problem. They are saying calculate the rate sensitivity for the material shown in the figure below at two strain value of epsilon equal to 0.05. So here they have given us the graph. So we need to use the graph to get our final value. But before we use the graph, we need to find the engineering stress and engineering strain in this case, right? Because the graph is given an engineering stress strain curve. We are not getting a true stress, true strain curve. And they have asked us true strain value related to that, right? So at true strain related to engineering strain by this formula. We already have derived it in previous class, right? So I can write 1 plus E to be equal to exponential of 0.05, or if I calculate, let me just calculate. So E is equal to 0.0512. Okay. Now corresponding to this value, E value, if we measure 0.0512 somewhere here, corresponding to this, if we measure the strain values, okay, at epsilon 1 dot equal to 10 power minus 3 second and epsilon 2 dot at 10 power minus 2 second, we will need to measure that engineering stress values. Okay, so let's just, I have already measured it and I've kept it, so we'll just use that directly. Okay, at 10 power minus 3 per second, we'll have around 820 MPa, and at 10 power minus 2 second per second, sorry, we'll have 850 MPa. Okay, so this is the stress value S1 and S2 that we can write. So now we need to find the true stresses corresponding to the particular these two engineering stress values. Okay, so my sigma 1 will be equal to S1 times 1 plus E, sigma 2 will be equal to S2 times 1 plus E, okay, let's just calculate. Sorry, did anyone, okay. So sigma 1 is equal to 851.525. Sigma 2 This is 893. Okay. So now we have the true stress values. We know how the flow stress is related to strain sensitivity, like strain rate, right? So using that relation, we can write sigma is equal to C times epsilon dot to the power m, right? So using this relation, we can write 851.525 is equal to C times 10 to the power minus 3 to the power m, right? And then 893.52 is equal to C to the power 10 to the power minus 2 to the power m. Okay, C into 10 to the power minus 2 to the power m. So if we divide these two equations by each other, we will get 893.52, sorry, divided by 851.525 is equal to 10 power minus 2 by 10 power minus 3. C will be cancelling out. So this is what we are getting. So from here we can calculate the value of m, right? M is what they have asked us finally. So let me just calculate. I get m is equal to log of 1.0493. So let me do that. So final answer is around 0.02. Okay, let's see if this is an option. Yes. So this is our value of m. Okay, so you can see how we have used all the equations that we have learned so far: true stress, true strain, engineering stress, engineering strain, and then finally followed it up with the equations that we learned today about strain rate, like how flow stress is depending on strain rate. So we have used all those equations and finally arrived at this expression. Okay. Now let's go to the next question. Determine the percentage increase in flow stress for 2 order increase in strain rate. That is epsilon 2 divided by epsilon 1 dot becomes equal to 100. Okay, so 2 orders. You're changing by 2 orders. At 440 degrees Celsius and 25 degrees Celsius. Use the data for commercially pure aluminium at constant true strain of 0.25 and assume that flow stress is approximately equal to sigma is equal to C epsilon dot to the power m. So they're just giving us the same relation. Okay. So they're asking us to find the percentage increase in flow stress for both the cases. Okay. So we can write that since the material follows this behavior, sigma is equal to C into epsilon dot to the power m. Since material follows this behavior, we can write sigma 1 is equal to 10.2, right? C is given 10.2 into epsilon 1 dot to the power 0.066, and sigma 2 is equal to 2.1 into epsilon 2 dot to the power 0.211, right? So if I divide them directly, I'll get sigma 1 by sigma 2 equal to some 10.2 divided by, sorry, I think I made a mistake here. I'll just take, yeah, we are checking only at 25 degrees Celsius. Sorry, there's no point in checking both the temperatures simultaneously because that won't give us the right answer. Yeah, at 25 degrees Celsius, the two values of flow stresses. So if we divide them, we'll get sigma. Let's do sigma 2 by sigma 1 because it's epsilon 2 dot by epsilon 1 dot, right? So we'll get epsilon 2 dot divided by epsilon 1 dot whole to the power 0.066, right? So we already have given, they have already given the relation that is equal to 100. So if I substitute that, I can get the relation between sigma 2 and sigma 1, which is equal to, let me just calculate. Is equal to 1.355. Okay. So here the flow stress, the change in flow stress is equal to 35 change in flow stress is around 35.5%. Okay, so this is the first case, the 25 degree case. Now we want to see in 440 degrees case, right? So in that case, sigma 1 is equal to again 2.1 times epsilon 1 dot to the power 0.211, and sigma 2 again 2.1 times epsilon 2 dot 0.21, right? So this is at 440 degrees Celsius, right? So again, if I substitute epsilon 2 divided by epsilon 1 dot is equal to 100, I'll get sigma 2 divided by sigma 1 is equal to 100 to the power 0.211, or that is equal to, just calculate, 2.64, which means that the change in flow stress is 164%. Change in flow stress is 164%. So here, if we have an option, the D, 35 and 164 is the right answer, right? So you have understood, right, how this value is directly helping us. We do not actually need even the C values. They have given us the C values in the question. We don't even need that to calculate the answer for this question. Okay. So I hope that much is clear. Let's move on to the next problem. So they are telling during hot deformation testing of a material, the temperature was increased from 100 degrees Celsius to 150 degrees Celsius. In order to maintain the same flow stress for deformation, the strain rate had to be increased by a factor of 100. The activation energy for mass transport mechanism will be, assuming Q is equal to it. No, it's not Q, it's R. I think. Question is little bit. Assuming R. So temperature increased from 100 to 150. Strain rate had to be increased by a factor of 100. So they are asking the activation energy, the Q value. Okay. So initial temperature is 100 degrees Celsius, or if we are writing it in Kelvin, let's write it as 373 Kelvin. Final temperature, because all calculations have to be done in Kelvin. So remember, whenever you are given the temperature in Celsius, convert that to Kelvin. Okay, 423 Kelvin. Okay, strain rate is increased by a factor of 100, right? So epsilon 2 dot, just like last time, by epsilon 1 dot is equal to 100. This we can note down. So we already have the Zener-Holloman equation, right? Z is equal to epsilon dot times, sorry, the exponential of Q by RT. So if we take epsilon 1, like if we take like two cases, let's say epsilon 1, Q1 and T1, and then epsilon 2, Q2 and T2. Now if we solve this, we will get Q is equal to, or let me just solve and show it to you. Let's take the exponent on this side, so this will become ln, right? So Q2 by Q1 Q2 by Q1. Actually, R becomes common. So, oh, actually, we don't have to divide this. One second. Sorry. If I take the same temperature Q directly, yeah, because activation energy will not change, right? So this is what I was making a mistake. So I'll directly get Q is equal to, I'll take the ln on the other side. So R times, because R is on the denominator, ln of epsilon 2 dot divided by epsilon 1 dot. Right. Now that makes sense. Okay. And then in denominator we'll have 1 by T1 minus 1 by T2. Yes. This is the correct expression. So if I substitute and solve 8.314, ln of this and this is ln of 100. Divided by 1 by 373 minus 1 by 423. Okay, so final expression for Q would be, let me just calculate. Yeah, so the final answer I'm getting is 159,528.33 joules, which is almost equal to 159 kilojoules. Let's see, there's an option. Yes. So this is the final answer. Okay. I hope you have understood how we have reached to the solution. So yeah, let's see the next question. Which of the following is true regarding Berger's vector? Is it same as slip vector? That is true. We have already said that, yeah, Berger's vector and slip vector are one and the same. Okay. It is the shortest lattice translation vector, again true. We have seen why that is the case. Direction along which displacement occurs? No, that is wrong. It need not be the direction along which displacement will occur. Okay. Displacement occurs in different directions, so that is not correct. And vector that closes the Berger circuit, that is correct. Okay. So these are the three options which are correct. Fourth one is not correct. Okay. Next question. They are telling the magnitude of Berger's vector for a simple cubic crystal with lattice parameter A. So simple cubic crystal structure, right? We need to find the shortest lattice translational vector. Okay, so if you draw simple cubic structure, how will it look like? Right, this is how simple cubic. So we have atoms only at the corners. So the closest distance between any two atoms, whether it's this or this, is A. Right, any two atoms you measure, the closest two atoms are always at a distance of A. Right, so the smallest lattice parameter, like the smallest lattice translation that can happen, is A only, right? So this is the correct option. I hope you have understood. Let me move this to the previous page. Yeah. The final question is, it shows a lattice with dislocation present in it. Okay. Below figure shows a lattice with dislocation present in it. Mark the correct option. Okay. They are saying which is screw, which is edge. They are asking which is screw and which is edge. Okay. Now there are so many hints that they have given. First is, of course, like how the dislocation looks. So here we can see that A looks like it has screw dislocation, right? Because you can see from the image itself that this point is giving like a screw kind of region, right? A twisting kind of region. That is one hint. While B is giving an extra half plane of atom. So this is an extra half plane. You can see that here. So that is another hint. So we can say that A is screw and B is edge, right? That is the correct option. There is one more hint that this question is giving you. Here they're saying the dislocation line is like this. This is the dislocation line, right? They have shown the dislocation line. The dislocation line is like this. In the first case, the Berger's vector B is given to be parallel to the dislocation line, right? While in the second case, the Berger's vector is perpendicular. Like here you can see it's perpendicular. In point B, you can see the arrows I've drawn. While at point A, it is parallel. This is the Berger's vector, this is the dislocation line. So from there, we can say that because it's parallel, it should be screw. So A is screw. The perpendicular case is edge, because it is showing the Berger's vector is parallel to the dislocation line. So that is another hint that is given to you. Okay. So with that, we will come to the end of today's discussion session. We have talked about plastic instability, the effect of strain rates on flow stresses. We also talked about dislocations, and then we saw some problems on how to solve those problems using the concept that we have studied. We will be further understanding the concept of dislocation. We will dive deep into that in the further classes, because that forms the crux of plasticity. This was just an initial glimpse into what dislocation is and what dislocation behavior looks like. But yes, we will be understanding that in much more detail in the upcoming classes. For now, yes, this is enough for this week's session, and I hope that you are able to understand all the concepts. If not, if there are any doubts, any clarifications that you would want me to explain, we can talk about that in the next class. With that, we will end today's session. Just a second. Yes, we'll end today's session. I thank everyone for joining in, and we'll meet again next time this week, like next week again, this time only. So till that time, let's say goodbye. Okay. So thank you everyone for attending.